Hello everyone, my name is Dr. Raj Dandekar. I graduated from IIT Madras with a BTech in Mechanical Engineering and completed my PhD from Massachusetts Institute of Technology MIT in Machine Learning. There is a lot of satisfaction in building an entire language model entirely from the ground up, building it entirely from scratch. And in this tutorial, I am going to show you how to build Gemma 3 270 million fully from scratch on your laptop. All you will need is access to A100 GPU on Google Colab. When people say open source, it's not truly open source, it's only open weights. So the whole aim of this video and subsequent videos in this series is to democratize this knowledge and show you how to build a end-to-end open source model right from dataset collection, tokenization, creating input output pairs, assembling the architecture, running the pre-training loop, running fine tuning. We'll do everything in this lecture. Uh, so thanks everyone. I hope you enjoy what I'm going to show you in the lecture. Hello everyone. So let's get started with this workshop. The main idea which I want to showcase through this workshop is essentially how I pre-trained Gemma 3 270 million from scratch and got decent inference results. So, if you are not aware, Gemma 3 270 million model was launched around 10 to 15 days back, and this launch immediately caught my attention because it's really a small language model. The number of parameters in the GPT-2 smallest version was around 124 million. So this can be approximately considered to be in that range. And if you look at GPT-4, it is supposed to have about a trillion parameters, right? So this is multiple order of magnitude smaller than large GPT based models and even Google's own Gemini models. So here you can see Gemma 3 270 million definitely comes in the small language model category. And this model is available as an open source version on Hugging Face. But it's not really open source, right? It can be called as an open weights model where they have you can essentially download the model weights, you can even get the tokenizer which they used, etc. But they don't show you the entire pre-training from scratch. My goal with this workshop is that I want to show you the end-to-end process of starting with the data set, doing the tokenization, creating input output pairs. Then we will assemble the Gemma 3 270 million architecture entirely from scratch, and we will do the full pre-training procedure, and we will ultimately do inference as well. I'll show you the Google Colab code file which we will be developing. It looks something like this. So step one is importing the data set, then we have tokenizing the data set, then we have creating input output batches. Then here is where we define the Gemma architecture really. And then finally we have the configuration, and then ultimately we have the pre-training step, and then I have inference. So as you can see, the inference results which I have got, I gave it a sentence: once upon a time there was a pumpkin, and the inference results are coherent English and they make a lot of sense once I tell you what the my data set was. So let's read out some of my inference right now. Once upon a time there was a pumpkin. This pumpkin was very special. It was a big special pumpkin because it was real. Everyone was so amazed by the green color, etc. If the prompt is a little girl went to the woods, we have a little girl went to the woods alone. She looked around and the animals had been playing a game. Then she said, I want to tell you a secret. So it's incredible, right? We have assembled this entire pipeline on Google Colab, and I've managed to run it on a single A100 GPU. I'll also show you the data set which I've used. Of course, it's not all the information on the internet because then it would have been difficult to train it on one A100. So my goal with this notebook is that all of you should feel truly empowered to run an end-to-end model starting from pre-training right till the inference. Because honestly, just having the model weights does not help too much. It's not really fully open source if you just have the model weights. So this tutorial is going to get highly detailed. I am going to walk you through every piece of the puzzle here. You can see here how I have assembled the Gemma 3 270 million architecture. I am going to explain the building blocks of the architecture itself. I will try to keep this tutorial as self-contained as possible, but it will be really great if you have some notion of what an attention mechanism is. Even if you don't know those details, and if you come into this tutorial completely new as a complete beginner, I will try to make it as self-contained as possible. So these are all the lecture notes which we plan to get through this workshop. My whole aim is that, let's say you have this nano gpt, right, by Karpathy, and the reason this repository became so popular is, again, it showed the entire pre-training from scratch. But ever since Nano GPT came out, not too much focus has been made towards end-to-end pipelines. So I'll make this end-to-end pipeline and I'll make the code completely available on GitHub. I'll share the link in the description, which all of you can take a look at. So let's get started now immediately. We have to get through all of these 6 steps. I hope the stage is set. So the context is clear regarding what we are planning to build over here. Okay. I plan to make a series where currently I'm showing Gemma 3 270 million. Later I'll show GPT OSS from scratch. After that I'll show Quen from scratch, and I'll also show Kimi K2 from scratch. Those will come subsequently as part of this whole series. So let's get started with our data set initially. I wanted to demonstrate this whole procedure on a data set which is not too broad, and data set should be specific on a particular domain. So what I went ahead with is I went ahead with this tiny stories dataset. And for those of you who are not familiar with the origins of this dataset, Tiny Stories was actually a paper which was released through the Microsoft Research Group, I believe, and they constructed a dataset which consisted of stories which 3 to 4 year old kids can understand. Okay, and based on this data set, they showed that we could train models as small as 10 million or 50 million, and these models can still generate coherent English. So the main thesis of this paper was, we can, if we have a data which is specific enough, we can get a model which has 10 million or 50 million parameters, which can still understand and learn the nuances of language. We don't need the model to have all the knowledge of the world for it to learn the English language. Even specific constrained data sets help the model to understand the form and the meaning of English language, right? So this is a very specific data set which they used, and it was also made available on Hugging Face. So if you check this Hugging Face Tiny Stories data set, you will see that it has around 2 million rows. So every row here corresponds to one story. So if you look at this first row here, that's one story. One day, a little girl named Lily found a needle in her room. She knew it was difficult to play with because it was sharp. Lily wanted to share the needle with her mom so she could sew a button on her shirt. Lily went to her mom and said, "Mom, I found this needle." So this is one story. This whole blue box which I have highlighted is one story. There will be 2 million such stories, and all the stories will be such that 3 to 4 year old kids can understand. The beauty of this data set is that it's specific, but it also contains enough for the model to understand the nuances of English language. Because even for 3 to 4 year old to construct stories, you need to make sure the grammar is proper, you have a lot of words in your vocabulary, so on and so forth. So this is my data set which we are going to use. Okay, and let's parallelly jump into our code as well. So this is the code file, and I've modularized it so that you can understand each step. So the first step is just importing the data set. So I'm going to run this right now, and I'm connected to the A100 GPU at the moment. Okay, so the datasets library is a Hugging Face library through which we can load the datasets provided through Hugging Face. For example, we have to load this Tiny Stories dataset, right? So it's important to install this datasets library. I'll again go ahead and make sure the library version is the most recent. And the main function which I'm going to use here is load dataset. And in this function, I'm going to pass this tiny stories data. So here you see, if you go to this link, datasets slash Ronan Eldan slash tiny stories, this is the link which I'm passing over here. And once I run this, my entire dataset will be loaded onto my Google Colab at the moment. So here you can see that 2 million rows will be downloaded over here, and it's pretty quick. It does not take too much space also. That's one advantage of using this data set. So my training data, so the whole data is split into training and testing. So I have my training data, which has around 2 million samples, and I have my testing data, which has about 20,000 samples. So overall, it comes to 2.2 million, let's say. Uh, so now the data set is loaded. So step number one is finished for us, where we have constructed the data set. Let's go to the next step now, which is dataset tokenization. I like to call tokenization as the neglected evil of large language models. And the reason is because almost everyone focuses on the cool aspects of language models, right? Assembling the architecture, pre training, inference. But no one really pays attention to tokenization, which is uncool, but it's extremely important. What is tokenization? Well, tokenization essentially is the art of converting text into numerical format so that the computer or the language model in our case can understand each pieces or each part of the text. So if you have one story here which looks like this, it as a human I can read it, right, because it's in English language. But a computer cannot really understand English language. It cannot really understand text. So we need to convert this text into a numerical format. And the process of converting text like this into numerical format is called as data tokenization. So we have a task at hand, and the task is we have these 2 million such rows for training and 20,000 such stories for validation, right? So if let's say I focus on one single story at the moment, uh, our goal is to do two things. We have to tokenize this story, which means that we'll need to convert it into individual elements, and then we'll assign a token ID to each of those individual elements, and then we'll have to store all of our token IDs somewhere. So later when we go to creation of input output pairs, the process of training, the model will no longer get these stories. It will just deal with token IDs. So currently we have to break our text into smaller individual components, which are the tokens. We have to assign a token ID to each token, and then we have to store all the token IDs in a single .bin file. Now, let's say, so the ultimate aim is something like this. If you have a story, right? If you have a story, I want to convert it into a set of token IDs. That's all. And then I will find the length of token IDs associated with each story. So each and every story I want to convert into a set of token IDs. So there's now here is where the first research question comes into picture, right? How would you convert a given piece of text into smaller individual pieces? And if you think about it, there are some things which naturally come to humans. The first thing which I might say is that, okay, I have this story, right? What if I break it down into individual characters? So I'll break each all the story into individual characters, which I'm highlighting on the screen right now. So let's say this is my story. Let's say this is my story, and I've broken that story into individual characters. And then I'll assign a number to each character. Maybe A is number one, B is number two, etc. So that's how my entire story can be converted into token IDs. For example, if you look at this story right now, let's say O comes at position 21, so 21, 18, this is 4, etc. That's how this entire thing will be converted to token IDs. But what's the issue with this approach? This approach is called as character level tokenization. There is one major issue with character level tokenization. You can pause this video here for a while if you want to think about this issue. So essentially that issue is called as ballooning effect. When you look at language models, they have something like a context, which is how many tokens they can process it at once before giving the answer. Think about you studying for an exam, right? There is a limit to amount of information which you can cram in at one time before producing answers. It's similar to language models. So if every piece of text is broken down into characters, the number of tokens which I have for every story will balloon. It will become huge in number. So it might happen that the LLM context window, which is the number of tokens the LLM can pay attention to at one time. When I say LLM, I mean language model. So if the number of tokens the LLM can pay attention to at one time is X, it might happen that within one story itself, the number of tokens which I have is 2 times X or 3 times X. That's very bad, because I need my entire story to fit within the context window of the language model. If my story does not fit within the context window, context is lost and answers will not be produced properly. This is one major issue with character level tokenization. It leads to the context window problem. The second issue of character level tokenization is that it really breaks or destroys the main essence of text. What do I mean, essence of text? So, all the advances in machine learning have happened because humans have exploited the structure of the underlying data. Why did CNNs work? Because convolutional neural networks exploited the structure of an image. Filter maps exploited the fact that, let's say, if you have a cat, two eyes will always stay close to each other. That spatial locality, right? They exploited these features of the image. That's why CNNs work compared to traditional neural networks on an image. So if you want to make a language model, character level tokenization completely destroys the meaning of the underlying text, right? Words carry meaning, they are similar to each other. For example, cat and kitten are similar to each other, right? But if I break every word into its individual characters, then the complete meaning is lost. I am just looking with a magnifying glass, and so it's like in a forest, you're inside a forest. So you don't actually see the patterns. Only when you zoom out, you see the patterns, right? So you're destroying the main essence of text when you break the text into character level. So we will not be going ahead with character level tokenization. The second type of tokenization is word based tokenization. That's also quite intuitive, right? What if I take every so in word based tokenization, what you have to do is you have to maintain a vocabulary. So let's say the vocabulary looks something like this, and I will assemble all the words in English language in this vocabulary. And then what I have to simply do is that whenever I encounter a word over here, let's say girl, I will find where this comes in my vocabulary, and I will look at the token ID associated with it. Let's say it's 1557. I will assign token ID of 1557 to girl. Similarly, I can, let's say I look at crab. I'll look at crab. I'll see where it comes in my vocabulary. If it's arranged alphabetically, it will come before girl. And I will see the token ID which is associated with crab. And I will assign it that particular token ID. Right? So it seems like a simple enough method. What's the issue with this? In fact, this seems to solve both of the issues with character level tokenization I mentioned, right? Now that we are doing word based tokenization, we won't have as many tokens as we would have had in character level. Also, we are not destroying the main essence of text since we are doing tokenization at a word level. So, what are the main issues with this? Again, you can pause this video for some time if you want to think about it. The main issue with word based tokenization like this is that it leads to something which is called as an out of vocabulary or an OOV problem. Imagine that you have a piece of text where a spelling mistake has been made. So, if a university is spelled as this, it's not obviously correct, right? In your vocabulary, this word will not find a place at all because it's not an English word. So, what will you assign to this? That's the out of vocabulary problem. This problem did not happen in character level tokenization because no matter whether there is a spelling mistake or not, every word can be broken down into individual characters, right? So that's the issue. That's the issue over here. We have the out of vocabulary problem. That's one issue. Second major issue is that if you take a look at English, right? Current everyday English has around 200,000 words or 200,000 tokens. And all, if you take all documented forms across history, that has around 600,000 tokens. And if you include scientific names and jargon, that has 1 million tokens. That just in the English language. If you want to build a multilingual language model, imagine the number of words you need to keep in your vocabulary. That's huge. And as we will see later, the more the vocabulary size you have, the more computationally expensive pre-training actually becomes. So we will not go ahead with word-based tokenization as well. There is a third tokenization scheme, which is the best of both worlds. That's called as the subword tokenization scheme. So subword tokenization scheme solves the issues which are present with both character as well as word level tokenization. The way subword tokenization works is that it starts with a vocabulary, and in the vocabulary we don't add words, but first let's say we add characters. We add only characters, and characters are limited in number, right? So we add all the characters, and then what we do is that in the data set we look at characters which are frequently occurring, and we merge these frequently occurring characters together. So let's say if you have words like token and tokenization. Now this ization is a group of characters which might come across in a number of places, right? So ization will be a separate token, and token will be a separate token. Similarly, if you have higher, this will rarely be one single token in byte pair encoding, because ER would come up in several places, right? So it's a commonly occurring character pair. So this ER becomes a separate token and high becomes a separate token. In fact, what you can do is that you can go to this interactive playground called Tick Tokenizer, and you can select the tokenizer here to GPT-2. GPT-2 had a subword tokenization scheme called byte pair encoding, and you can take any, let's say I go to this movie Inception, and I take the description of this movie Inception over here. I copy all of this and I paste it over here. So just take a look at the tokens over here, right? Now this infiltrating is not one full token. In fact, ating is another token, because maybe ating shows up as a suffix in many other words, and infilt is a separate token. So we don't need to have every single word in the English language as a separate token in the vocabulary. Highest, so he is a separate token, ist is a separate token. These characters which show up frequently, they are merged into separate tokens, right? You can see many instances. So for example, stealers. Now ers might appear several times in other words also. So steal is one token and ers is a separate token. That's what subword tokenization does, and this reduces the vocabulary size a lot, because I don't need to now save each and every single word. If a word has a common prefix or suffix, I have already saved it as a separate token. So one common way to do this subword tokenization scheme is called byte pair encoding, where you merge frequently occurring characters and keep them as separate tokens. What byte pair encoding does is that it reduces the vocabulary size compared to word-based encoding. We don't have any out of vocabulary problem also, because characters are anyway there in our vocabulary. So out of vocabulary problem is not there, and we don't have a context problem also, because not apart from characters we also have subwords and words in this vocabulary. So this subword tokenization scheme is one of the most popular tokenization schemes, and this is what we are going to implement in our code. We are going to take every single story and we are going to implement this subword tokenization scheme called byte pair encoding. And so subwords can be individual tokens. The vocabulary size which we are going to consider is 50257. Uh, yes, so the vocabulary size which we are going to consider is 50257, and the library which we are going to use for tokenization is called as tick token. This is a byte pair encoding tokenizer where if you give data, it converts it into subword tokens based on byte pair encoding. And in byte pair encoding, we have to specify a vocabulary size. I'm going to go with GPT-2 vocabulary size, which is 50257. So if you go to GPT-2 vocabulary, right? Let's see if they have their vocabulary somewhere. I remember seeing it at some point. Yeah, this is the main byte pair encoding code. GPT-2 vocabulary size. So GPT-2 vocabulary size is 50257, correct. So this is the size which we are going to use. Now, Gemma, right, when they released Gemma 3 270 million, they have not specified the data on which they trained their tokenizer. But their tokenizer size is 262144, or their vocab size, I should call it. Gemma 3 270 million vocab size is 262144. But for the sake of simplicity, we are going to use a vocabulary size of 50257. I think they might be using a subword tokenization scheme itself, such as byte pair encoding, but the vocabulary size they have used is much higher. Typically, higher vocabulary size leads to higher compute, more number of trainable parameters, etc. So we will go ahead with byte pair encoding implemented through tick token library, and the vocabulary size we are going to use is 50257. Okay. So first part of this, I think we have understood that we are going to look at individual stories. We are going to convert every story into token IDs based on the subword tokenization scheme. So story 1 will have these token IDs, story 2 will have these token IDs, etc. Then what I have to do is that I have to store these token IDs, right? Because later when we are looking at input output pairs, we need to assign token IDs to word. So I need to store all of my token IDs somewhere, because I will create my input output pairs from my token IDs. So currently imagine that you have a bunch of stories, and stories have been converted into token IDs. Um, but I also want to store my token IDs, because these token IDs are from where I will get my input output pairs. Now we are going to implement a smart strategy when storing these token IDs. I am going to store all my token IDs on disk rather than saving it in my memory. So the way to do it is that we are going to create a file which is a .bin file. So we are going to create a train.bin file, and we are going to create a validation.bin file, and we are going to save these files on disk. The reason we are going to save it on disk is because it leads to fast data loading during training, no need to retokenize, and avoids RAM overload on big data sets. So the way we will do this is that we will, let's say, get all of our token IDs, we'll convert them into batches, and then we'll write all of these token IDs into a train.bin file. So imagine all of the token IDs which you have got here from the training data. You'll collect them all together. You'll break it into batches, and each batch will be written to this train.bin file. So the way I ensure that my file is saved on disk is because I will create a np.mem map, means that the file is backed on disk. It looks like a numpy array, but it will be backed on my disk when we create a memory mapped array. You will see this when we code right now. So I'll create one training.bin and I'll create one validation.bin. Essentially, imagine that at the end of this step, we have two big bags. One bag has a collection of token IDs, train.bin, and another bag has a collection of token IDs in validation.bin. So it's all the token IDs dumped together. So we got this data set, we got each story, we converted into token IDs, we dumped all the token IDs together in the train.bin file and in the validation.bin file, both on the disk. So now you should appreciate how language modeling works after this point, right? Because for the computer or for the AI or language model, whatever you call it, it just has these bags of token IDs. We do not tell anything about meaning. We do not tell anything about grammar. It has to decipher everything on its own from the architecture which we are going to now design. That's the beauty of language modeling, in my opinion. So let's go to code now and finish step number two. In step number two, we are doing the tokenization, right? So as I mentioned, we are going to use tick token library and we are going to use the GPT-2 encoder so that we have a vocabulary size of 50257. The first thing what we are going to do is that we are going to define this process function. What it does is that it takes my any example or text which I have and converts it into token IDs and the length. So this is very similar to what I showed you in the code. Every story will have a bunch of token IDs associated with it and the number of token IDs or the length. That's what this process function actually does. So what we do is first we call this process function and every story is mapped to the token IDs and the length or the number of token IDs. And here is where the np.mem map. So we create a train.bin and a validation.bin. And here is where we break the entire all the token IDs into batches and then we create or we get the batch and we write it into our array. Similarly, we loop over all the batches. So this for loop is exactly what I mentioned over here. Right here, we get the batches and we write them into the train.bin file. That's this for loop over here. Okay. So just run this right now. And here you will see the reason I'm paying so much time on whether the file is backed onto memory or disk is because if you don't do this np.memmap, right, it will take a huge amount of time for you to do this tokenization step. Even right now it takes some time, right? So this is still tokenizing, it's not begun the writing process yet. This tokenizing the splits is the first part where we are converting every story into token IDs. The writing process is the one which takes time. After this is done, the writing process will begin where we have these 1024 batches. Each batch will be written and that file will be stored. Train.bin will be stored and validation.bin will be stored. Remember, after this step, we'll just have two bags like this. One training.bin, train.bin, that's the collection of training token IDs, and one validation val.bin, which is the collection of the validation token IDs. So now the split tokenization is happening and it's around, yeah, it's fully finished. So until this point, the stories are converted to token IDs. But now the computationally heavy or time intensive step will start where we'll actually begin writing the train.bin and the validation.bin files. So you'll see that that is the most time consuming step. One exercise which I would like all of you to do is just remove this np.mem map and make it a normal array and see the amount of time which it takes. See, now it's starting to write the files, right? And it's showing that it will take around 15 minutes. So let this run right now. And meanwhile, let me go to step number 3, which is creation of input output pairs. Creation of input output pairs is probably one of the most important steps in understanding how a language model functions. When we have a classification problem, when we have a regression problem, we have supervised learning, right? Inputs are given to us, let's say images of MRI scans. Those are the inputs, and the output might be whether a brain tumor is present or not. So input output pairs are very obvious to see. If you are predicting the price of a house, let's say the inputs are the area of the house, um, locality where it's present, number of bedrooms, number of bathrooms, etc. It's very easy to think. But when you're creating a language model, the task which you're training the language model for is the next token prediction task. You want the language model to look at a set of tokens and predict the next tokens. The way input output pairs are created is actually very interesting. Let me show you how. Let's say if you have a story which looks like this. One day, a little girl named Lily found a needle in her room. She knew it was difficult to play with it because it was sharp, etc. That's one full story. And I want to create input output pairs. So, when I say input, This will be the input which will be passed to my language model. And when I say output over here, that's the ground truth. So that's the correct data, the next token prediction task. So to create an input pair or to create an input output pair, I need to know first thing what's the context size, which is what's the number of tokens which the model can look at one time. If the context size is 4, what I do is, so one day a little, let's say I take 4 tokens. That's my first input sequence. So one day a little corresponding to token ID 1, 11, 15, and 24. To create the ground truth or to create the output data for this input sequence, we simply shift it to the right hand side by 1. So the ground truth for this input sequence is going to be day a little girl, which has token IDs 11, 15, 24, and 63. That is my first input output pair, which I have written also over here. My first input sequence is one day a little, corresponding to token IDs 11, 1, 11, 15, and 24. My first output sequence is shifted to the right by 1. So day a little girl, corresponding to token IDs 11, 15, 24, and 63. Now, you might be thinking, why is this input and target? What's the input and what's the output actually? So this looks like one input output pairs, right? But within this, there are actually 4 prediction tasks. Why are there 4 prediction tasks? So prediction task 1 is that if 1 is the input, I want day to be the output because we are doing next token prediction. If one day is the input, if one day is the input, I want A to be the output. If one day A is the input, I want little to be the output. If one day A is the input, I want little to be the output. And finally, if one day a little is the input, so this whole thing is the input, I want 63 or the girl to be the output. So in this one input output pairs, there are 4 prediction tasks through which we are ensuring that the model predicts the next token correctly. So whatever I have marked in the dotted box right now is the ground truth. We want these to be the answers. So when this is the input sequence, this should be the answer, etc. So at all times we are ensuring that the next token which is predicted is correct. Now this type of learning, it is neither supervised nor it's unsupervised, because the model is creating labels on its own, right? We provide the input, the model itself shifts it to the right hand side by 1. So the model creates labels on its own, that's why it's called as self supervised. And the reason it's called auto-regressive is because the output of the first task is added as an input to the next task. The output of the second task is added as an input to the next task. The output of the third task is added as an input to the next task, etc. That is why when you train language models, people say that it's just a next token prediction task. Because even when you look at one input output pair, at each point we are just training the language model to predict the next token correctly. So one parameter which we already looked at is context size, which we need to determine to get the input sequence length. But we also need to determine the batch size. That means how many input output pairs we are going to look at before we update the gradients. We need to know what's the batch size. So in this case, I've assumed the batch size to be equal to 4, right? Where we have 4 input and output sequences in one batch. So what is done is that from random places you get inputs and then shift it to the right hand side by 1. So if I want one whole batch, I will need to have 4 inputs. Let's say one input is this, second is this, third is this, and fourth is this. And then in a self supervised way, I get the output by shifting the inputs to the right hand side by 1. So these 4 input output pairs which I'm showing on the screen right now, that constitutes one batch. And for each input output sequence of the batch, there are 4 prediction tasks. Why 4? Because that's the context size. The number of input, the number of tokens we have in the input sequence, we have those many prediction tasks in one input output pair. Okay. So when we assemble the language model architecture, when we assemble this Gemma 3 270 million architecture, these input sequences, whatever is the matrix here, that will pass into my architecture and I will get some output. Of course, all of, let's say I look at one input sequence, I will pass it into my architecture and I get some output. Of course, the output won't look like this initially. I want the output to look like this when the model is fully trained. So I will fine tune the parameters, or I will, in the back propagation, we will train the parameters so that the output starts looking as close to the ground truth as possible. So we will aim our model predictions to be as close to the ground truth as possible. And then the loss will be some measure of the ground truth minus the prediction. That's the cross entropy loss. I hope all of you have understood this step, which is very important. If you're given a piece of data, how do you create input output sequences? The first thing to note is what's my context size or input sequence length, and what's my batch size. Once these two are determined, you can get, for one batch you can assemble inputs like this, and for to get the output you just shift the input to the right hand side by one. All right, and then for each row, so if you look at the first row, that's one input and output sequence. Within that there are four prediction tasks, uh, similarly for all the other rows. So for every input sequence you know what the output should be, and eventually we'll train an LLM to predict these outputs which are present in our ground truth. Okay, there are some things in the code which I have mentioned over here. So, for example, in the code, we'll see something like x.pin memory. The whole purpose of this pin memory is that it locks the memory of tensor in the RAM. This allows faster transfer to the GPU. It's like saying, don't move the memory around, GPU would want it soon. Then, what we have done is that we have also made this non-blocking equal to true. So usually this two device, right? When we do two device, it blocks the CPU until copy to GPU finishes. When we do non-blocking equal to true, it ensures that CPU can continue to do other work like next batch preparation, etc. So all of these operations are just done to make sure that things happen in a much faster and smoother manner. In the code, you will also notice that this rand int, so that means that the input sequences, these green sequences, are chosen randomly from the data set. So when there is, so we will write a function which is called as get batch. When we call that get batch function, input sequences will be chosen randomly and output sequences will just be input shifted to the right hand side by one. So this train.bin which I showed you earlier, it's still ongoing. See, that's why I mentioned to you that it's a pretty time expensive process. But while this is happening, we can take a look at the create input and output batches, right? So as I mentioned, we'll define this get batch function. It will create one input. So it will create an input tensor and it will create an output tensor for one batch. That's what this get batch function will be doing, right? And this function will need two things. We'll need block size and batch size. So block size is what I refer to as context length or input sequence length here. What I refer to as size or input sequence length, that's equal to the block size, and batch size is just going to be the size of the batch, right? So we are going to randomly take, let's say if our batch size is 4, we are going to take 4 indices that will give us 4 input sequences randomly scattered throughout the data. So these four green boxes which I've shown. Then what will happen is we'll create the inputs, and then y, which is the outputs, will be the inputs which are shifted to the right hand side by 1. That's how we'll create the input output pairs. And this is the pin memory which we defined. That's all. So this get batch function is actually extremely simple. It just gets the input batch, it shifts the input batch to the right hand side by 1, and then it gets the output batch. So let's quickly recap what all we have seen so far in assembling the Gemma 3 270 million model. We have seen these three steps which are often neglected. And when people say open source, they only focus on step number 4 essentially, which is sharing the model weights. But the first step 1, step 2, and step 3 are often neglected. So I thought it would be a good introduction to this workshop by explaining about all these three. Step 1 is assembly of our data set. Step 2 is tokenization. We saw that we are going to use subword tokenization as compared to character or word based tokenization because it solves three things for us. It has low vocabulary size, which is computationally good. It solves the out of vocabulary problem, and it also does not lead to this ballooning issue which is associated with character tokenization. We are going to use the tick token library, and from this we use the GPT-2 encoding, which is the byte pair encoding. We saw that Gemma3 actually uses a vocabulary size of 26244, which is much higher than the vocabulary size of 50257, which we'll be using. They have given their tokenizer model, but they have not again mentioned here on what data set their tokenizer was trained on. Remember, the tokenizer also needs to be trained on some data set, right? Currently, we are also not training our tokenizer from scratch. We are already using the GPT-2 based tokenizer given from tick token essentially. And then the last thing which we have seen is creation of input output pairs, where we saw that ultimately we want to pass the input into some architecture and get the prediction and compare it with some ground truth, right? That's what happens in all of machine learning, whether you have regression, classification, anything. Here, I told you how when we have a data set, and now remember the model does not see sentences like how I am seeing right now or how you are seeing right now. For the model, it only sees these bags of token IDs. It only sees a bunch of token IDs. From these token IDs, it has to make these input output pairs. So for that, it needs two things. It needs a batch size and it needs a context size or the input sequence length. So that way you get the input batch. Let me call this X. Uh, this is X, which is the input batch, and then we get the output batch, which is shifted to the right hand side by one. That's the next token prediction task. I hope all of you are ready. In the next step, what we are going to see is that we are going to assemble the Gemma architecture. And then we are going to see how this input will pass through this architecture and how it will get us the predictions, which we will ultimately compare to this output, which is the ground truth. Meanwhile, I can see that my initial step of training.bin and validation.bin has finally finished. It took around 15 minutes, by the way. So if you don't do this memory mapping, it will take even more time if you just save everything on RAM. All right, so now let's move to the next step, which is essentially assembling the Gemma architecture. Next, we come to an aspect which can be called as the brain of Gemma 3 270 million, and this is probably the most important section of this video. So you can pay very careful attention to this section which I'm explaining right now. I've tried to make it as visual as possible so that you will be able to understand each and every single aspect. If you have never seen a transformer architecture before, some of these terminologies might be new to you, and you might need to go back and revise some key fundamentals. For example, if you don't know what a query is, what a key is, or what a value vector is, I'm assuming that you have some basic knowledge of these. But even if you don't, for now, try to follow along so that you get an entire overview of the Gemma 3 270 million architecture. So, if you think of their architecture, it can be broken down into three parts. There is the input part, there is the processor part, and then there is the output part. Different things happen in each part. In the input part, I can say that there are two main things which happen. If you have an input sequence, so right now, all the thing which we are doing is we are saying that this input sequence, it passes through this entire architecture and something comes out, right? So, this is my input right now. This is my input, this is my input sequence, and it will go through this journey, which I will explain to you now. It will go through this long journey in the LLM in the Gemma architecture, and an output will come out. Okay, so what happens to this input? First, these input tokens are converted into token IDs. We have already seen this part, so this part is already done. Okay, then there is something called token embeddings, which also happen in the input block. Once the token IDs are converted into embeddings, these embedding vectors pass into the processor block. So they start from this RMS norm module, they go to the sliding window module, go to another RMS norm, then one more RMS norm, then feed forward neural network, and then another RMS norm. There is a skip connection here, and there is a skip connection over here. I'll explain each of these individual modules to you separately, but no need to worry about it. The attention mechanism, which is where all the magic happens, where context is retained, and that's why language models are able to answer questions so well, is these three parts. Now, compared to the traditional multi-head attention mechanism, Gemma 3 270 million made several changes. First of which is having something called a sliding window attention. Second is having rotary positional encodings. Now, many modern architectures in language models do use rotary positional encodings, but earlier, let's say GPT-2, they used absolute positional encodings. I'll show that also. And then they use query key normalization. At several places, you will see RMS norm. This is also a bit of a change, right? Earlier, so when GPT-2 models came out, they used a normalization, which is just subtracting the mean and dividing by the square root of variance. RMS norm is something which is a bit different, and many modern architectures have started to use this. The feed forward neural network of Gemma is also a bit different than the way GPT-2 did it. And then once we come out of this, remember that this whole thing which I'm showing right now, it's one transformer block. Gemma 3 270 million had 18 such transformer blocks stacked sequentially, right? So once this input tokens go through the token embedding, they go through one transformer block, then they go through the second, they go through the third, they go through 18 transformer blocks. Then the input IDs come out, and then they go through the output layer. They go through the RMS norm, and then finally what comes out is the next tokens which are predicted. These next tokens which are predicted will be ultimately compared to these output tokens, right? And then we'll get the loss and we'll see everything which happens after that. But this is the broad bird's eye view of how the architecture works: input, processor, and output. Now what I'm going to do is that I'm going to explain to you some key modules so that you understand the whole architecture. The first thing which you need to understand is what exactly are embeddings, which I've mentioned over here. Second thing which you need to understand is RMS norm and how does it work. Third thing which I'm going to spend a lot of time on is everything related to attention, right? What is this multi-query attention which I'm talking about? Then what is this sliding window attention? I'll also explain what is sliding attention. Then what are rotary positional encodings? What is QK norm? What are the changes in the feed forward neural network? I'll explain that also. And finally, I'll explain the output layer. Okay. So let's go on a journey together and try to understand each and every one of these building blocks. The first thing to understand is token embeddings. And the whole idea of token embeddings can be originated to this paper called Word to Vec, which essentially proved that words can be represented as vectors to capture their full meaning, right? So there is a beautiful token embeddings. There is a beautiful blog actually, which we have written recently. Um, yeah, it's this. And here, as you can see, let's take a look at this GIF which I'm showing on the screen right now. These are words which are represented as vectors. Now, the beauty here is that words which carry similar meaning, like fruits, apple, and mango, they will be closer together in vector space. And initially, when the vectors are initialized randomly, the vectors won't carry any meaning. But as the vectors are trained, apple and mango have a similar meaning, so they will be closer to each other, right? So essentially what is done in this step is that token IDs are converted into high dimensional vectors. I am going to take you through the mathematics also later, but right now just think of it as a high level representation that token IDs are converted into high dimensional vectors so that they can encode meaning. And remember that we are not using any pre-trained models here. These token IDs are randomly converted into vectors. We are going to learn these vector representations so that they carry meaning. So these are also trainable parameters. I'm just going to mark it as P wherever we have trainable parameters. Okay. So words can be represented as vectors and vectors can encode meaning in higher dimensional spaces. That's the first thing which is done here. Token IDs are converted into embedding vectors. That's the first building block. The second building block is RMS norm. And the best way to explain how RMS norm operates is to explain these 5 steps. Let's say if you have a vector, right? The first thing what you do is that you take a square of all of these elements and divide by the number of elements, and then you take a square root. This epsilon is added just to make sure that things are not divided by 0. But this term here, which is square root of the variance plus epsilon, uh, is the RMS or root mean square. And then the normalization works like this: every element of this vector will be divided by this RMS value. That's all. So essentially, if you have x1, x2, and x3, the RMS is just going to be square root of 1 by 3 x1 square plus x2 square plus x3 square. So if this is my vector, then the RMS norm is just x1, x2, x3 divided by this. That's the RMS norm. Now, when you use LLMs or language models, they apply some scale and shift parameters as free parameters or trainable parameters, just so that if you want to shift or scale the vector. So these are trainable parameters. You take this normalized vector, you multiply with 1 plus some scale parameter, and then you add a shift parameter. These are also trainable. So I'll mark these scale and shift parameters as P. Usually, when people think of the normalization step, they think that it does not have trainable parameters, but that's not quite true. The scale and shift parameters in normalization are trainable. So if you take a simple example, if this is my input vector 2 and minus 6, right? If my scale parameters are zero point 0.5 and minus 2, minus zero point 0.2, and if my shift is 1 and minus 1, first I get the variance or VAR, which is 1 by 2, 2 square plus 6 square, which is 20. So RMS is square root of this VAR, which is 4.472. So the normalized vector is now dividing all the entries with 4.472. That's my normalized vector. And then what I'll do is I'll apply the scale and shift parameters, right? So what I do is I first multiply with 1 plus the scale parameter. So 1 plus scale is 1.5 comma zero point 0.8, and this symbol is element wise multiplication. So I'll multiply the first element here with the first element of this vector, and I'll multiply the second element here with the second element. So that's how I get the vector after scaling. And then after this point, what I'm going to do is add a shift. So the shift is 1 and minus 1, right? So I add, and this is also element wise shifting. So I add 1 comma minus 1 here. So the final answer is 1.671 comma minus 2.074. So wherever you see RMS norm in this architecture, it's this simple operation which is applied to a vector. So this vector which you are looking at right now, it will be a higher dimensional vector. I'm going to go through the exact dimensions which Gemma actually used, but for now I want to give you a conceptual understanding so that it becomes clear. Okay, so this is RMS or a root mean square normalization. And you might be thinking, why are these scale and shift terms added? So the simplest explanation is this is what humans have been doing ever since DeepSeek was invented, right? If we cannot figure some things out, we make them trainable parameters and offload it to optimization or back propagation. So without adding these bias terms, sometimes our accuracy might not be good, our performance might not be good. So it turns out that just introducing a few free parameters helps. And remember that this RMS norm term, which is mentioned once here, actually in one transformer block, it's mentioned 1, 2, 3, 4 times, right? In one transformer block, 1, 2, 3, and 4. There will be 18 such transformer blocks. So just keep that into mind. So these are the first two things, which is the embedding vector and the RMS normalization. Now we are going to come to the most important part, which is where all the magic happens, and that's the attention mechanism. Now, before actually going to what is multi-query attention, let me do a summary of what exactly is multi-head attention, so that all of you understand when we come to multi-query. So let's say these are my inputs, right? The artist painted the portrait of a woman with a brush. And as I have told you before, we are going to convert the input into embedding vectors. So these will be higher dimensional vectors when they enter the transformer block. So let's say these are 8-dimensional vectors for now. Okay, the way the multi-head attention mechanism works is that, let's say this is the input matrix right now, which has 11 rows and 8 columns. I'll be multiplying it with a trainable query matrix, a trainable key matrix, and the trainable value matrix. So these are also free parameters here. All of these parameters are not known beforehand. It's some, so again here humans have offloaded the training here, because if we did not figure out how to capture the context between inputs, the best way to do that is have some trainable matrices, and hopefully these matrices are trained such that the context between inputs is recovered. Okay, so each token right now has an embedding vector which is associated with it, and before these all these tokens enter the transformer block, these tokens have actually no clue about who their neighbors are. These tokens have no clue who their neighbors are, because all the operations on these tokens have been done at a token level. It is in this multi-head attention mechanism where these tokens actually start to know who my neighbors are, and they start to understand how much attention should I pay to each of my neighbors. And the way it happens is as follows: you have this input embedding matrix, right? And if the dimensions are 11 comma 8, the row dimension of the trainable query key and value weight matrix has to be 8, because this multiplication needs to go through. But the column dimension can be anything, so you can think of this as an output dimension. So when you multiply the input with WQ, WK, and WV, you get these query vectors. So the query vector matrix is 11 comma 4, key vector matrix is 11 comma 4, and the value vector matrix is 11 comma 4. And here D out is equal to 4, which is the output dimension. Now what is done is that this is single head attention, what I have just shown you right now. In multi-head attention, the query matrix, the trainable query matrix is split into two heads. The trainable key matrix is split into two heads, and the trainable value matrix is also split into two heads. So when you multiply X, now you have WQ1, WQ2, WK1, WK2, WV1, WV2. So these are the queries, keys, and values of head number 1, and these are the queries, keys, and values of head number 2, right? So when this multiplication is done, you have the query vector, key vector, and value vector associated with head number 1, and you have the query vector, the key vector, and the value vector which is associated with head number 2. Naturally, the head dimension is now equal to the output dimension, which is equal to 4 divided by the total number of heads. So the head dimension is equal to 4 divided by 2, which is equal to 2, since the number of columns for each head is equal to 2. And remember, I mentioned that this is the step where every token gets to know about its neighbors. The way it happens is that, let's say if you look at head number 1, you have this query vector, right? This is multiplied with the keys transpose. So if the query vector is 11 comma 2, the keys transpose is 2 comma 11. So you have an attention scores which is 11 comma 11, and this attention score actually carries meaning. So these are 11 tokens, right? So this is the artist, etc. These are 11 tokens, and here also these are 11 tokens. So every single value here, if you look at this value, it carries the attention score between the artist painted the, so the, and so it carries the value between the fourth token and the fourth token. This value, this carries the attention score between 1 2 3 4 5 6 7 1 2 3 4 5 6 7 eighth token, and 1 2 3 4 5 6 7 8 ninth token. So this carries the attention score between the eighth token and the ninth token, which is woman and with, right? So essentially these attention scores all carry a different meaning, which is very important to understand. And let me show you here. This is what I mean. This is the 11 by 11 attention matrix, right? So if you see this, it carries the attention score between artist and painted. If you see this, it carries the attention score between portrait and woman. If you see this, it carries the attention score between with and brush. So that's why I mentioned that in the attention block, this is where tokens get to know about their neighbors. So if a token wants to pay attention to its neighbor, its attention score will be high. So remember that now since we have two heads, every head will have its own attention scores matrix. So the first head will have an 11 by 11 attention score matrix, and the second head will also have an 11 by 11 attention scores matrix. Once we have the attention scores which are computed like this, we do two operations. The first is scaling, which is dividing by the square root of the keys dimension, and the second is essentially applying softmax. So the softmax ensures that all of these, if you take a look at each row, the each row sums up to 1, so you can assign probabilities that way. So we have attention scores, right? After applying these operations, attention scores will get converted to attention weights. One more thing to mention here is causal attention. Essentially, if you take a look at the attention scores, right? If you take a look at the attention scores matrix here, technically, if you want to predict the next token, you should not peep into the future, right? So if you take a look at painted, and if you want to predict the next token, you should not know what comes after painted. So painted should only have access to the previous two tokens, right? So that way, if you see, we actually mask out all the tokens, all the attentions weights which come above this diagonal. So this actually ensures that we do not peep into the future. For example, if you look at this third token, why should we know the attention score between the third token and the fourth token? Because the fourth token comes after the third token, right? So that's irrelevant. So when we look at the third token, all these scores are irrelevant. So we put them to 0. But when we look at the 10th token, for example, we should look at all the tokens which come before it. So until this point. So all the tokens which now come after the 10th token are irrelevant. So all these gray dots are irrelevant for me. They will be put to 0. This is called as the causal attention mask. So all the gray dots are essentially put to 0 because I cannot peep into the future. So for a given token, I only need to calculate the attention scores with respect to tokens which come before that token, right? So I get this attention weights matrix now with respect to head number 1, and I also get this attention weights matrix now with respect to head number 2. And the last step is multiplying the attention weights with the value vectors. So as the keys and the queries are split into half, you will see that the value vectors are also split into half, right? V1 and V2. So the last step is to actually multiply the head 1 attention weights with V1. That gives me the head 1 context matrix. And you multiply the head 2 attention weights with V2. That gives you the head 2 context matrix. And finally, these two context matrices you merge together, that gives you the final context matrix, which is 11, 4. This is the final matrix which come out of the attention mechanism. And now if you take a look at this input embedding which went into the attention mechanism, every row here corresponds to a vector only associated with that token. But now that thing changes over. If you take a look at artist, right, this is not just the token embedding of artist, it also contains information of how much importance needs to be paid to other tokens. This mechanism is the heart and the brain through which uh, transformers retain context. So the reason it's called a context vector is because every token has information of how much attention needs to be paid to the nearby tokens. And the reason we do multi-head attention mechanism is because every head captures a different perspective. So since the attention scores for head 1 and head 2 are different, head 1 context matrix will be different from head 2 context matrix, right? So every head can capture a different perspective. Why do we need a different perspective? Because consider this text which we have been looking at. The artist painted the portrait of a woman with a brush. This can have two meanings, right? The artist painted it the artist painted the portrait of a woman and the artist used the brush, or the artist painted the portrait of a woman with a brush. Two different meanings, right? So two different perspectives. So each attention head helps to capture one perspective that way. This is the entire attention mechanism which I've just explained to you. We start with the input embedding vector and we come out with a context vector. And the reason it's called as multi-head attention is because every head has its own attention scores matrix and every head captures its own perspective. Now, one thing which I want to mention to you is that if you look at this multi-head attention mechanism, right, and if there are, let's say, four attention heads, if you look at WQ, if you look at WK, this is WK1, K2, K3, and K4, right? Each of these have different values, right? Head 1, of course, has different values than head 2. Head 2 has different values than head 3, and head 3 has different values than head 4. That's why I've shown these with different colors. Similarly, WQ and WW, we also have different values with respect to each other. All the heads have different values, which I've shown with different color over here. Because why should they have the same value? I want to capture different perspectives by each attention heads, right? So it makes sense for different heads to have different values. This is multi-head attention. In multi-query, so this is multi-head attention. In multi-query attention, a kind of trick is done to prevent or to save computational cost. So in multi-query attention, what is actually done is that the same content is shared across all the heads. So if you see, head 1 has the exact same values as head 2. Head 2 has the exact same values as head 3. Head 3 has the exact same values as head number 4. Similarly, for the values matrix also, head number 1 has the same values as head number 2. Head number 2 has the same values as head 3. Head 3 has the same values as head number 4. Uh, you might be thinking, why is this even done? The reason this is done is two reasons. First, it reduces the size of something called as kv cache. We did not get into this in too much detail. And second, which is the more intuitive reason to all of you right now, is that it reduces the number of trainable parameters which we have, because we just share the parameters across the different attention heads. That's why it's called as multi-query attention. In the queries matrix, Q1, Q2, Q3, Q4 are different. We don't share values across heads for the query matrix, but for the keys and the values matrix, the content is actually shared across the heads. That is why this is called as multi-query attention. And Gemma 270 billion implemented multi-query attention, which means that when you look at one transformer block and when you look at the attention heads within that transformer block, the trainable key matrix and the trainable value matrix shared the same content across different heads. That's what is meant by multi-query attention. And of course, it comes with its trade-offs, right? Different values in keys and values ensure that every head captures a new perspective, a different perspective. But here the trade-off is you save computational time at the expense of maybe performance degradation. That's multi-query attention. And the second major innovation which they have did, which now many language models have started to implement, is called as sliding attention. So sliding attention is very closely related to the causal mask which we saw over here right now. If you remember what we looked at in the causal attention mask, you will see that every token essentially can only look at tokens which came before it, not after it. Right? That's why all the elements above the diagonal are set to 0. So this is the causal full attention causal mask where every token can just look at what comes before it. So it cannot peek into the future. What sliding attention does is that every token can not only not peek into the future, but it cannot also look too far back into the past. So for example, now this token, right? It cannot peep into the future, sure, so it does not have access to this. But in sliding attention, it does not even have access to these tokens which come way before it. It only has access to two or three tokens which come before it. So this window in which tokens have access to only a certain window of tokens which comes before the current token, this is the sliding window amount which we have to define beforehand. And this was defined in Gemma for sure. I'll come to what these values were exactly. Actually, in Gemma, the sliding window was 512, and their input sequence size was 32768, right? Now, if you use a full causal layer, you have to essentially compute 32768 into 32768 attention scores, or order of n square, not exactly n square because you are essentially putting these to 0, but on an order of n square divided by 2, I think. You need to compute these many attention scores. But now if you do something like this, right, where if you restrict every token to only look at a certain number of tokens which come before it. So for example, if you are at position number 6, it can only look at tokens 5, 4 and 3, 3 tokens. If you are at position number 5, it can only look at 4, 3 and 2, these. That's where this band actually forms. So if you take a look at this band over here, this red band, these are the only allowable tokens we are allowed to look back into. That's why this is called a sliding window, right? Because essentially this window, you are sliding to the right, you're sliding to the left actually. And this reduces the number of attention scores which we need to calculate by a huge amount. So here I am showing an 8 by 8 matrix, right? If the number of input, if the number of tokens in the input sequence are 32768, like was the case for Gemma 2, if you actually use the causal attention, you will need to compute n square by 2 attention scores. But if you use the sliding attention, you only need to calculate or the order of n into w, and that is roughly 32768 divided by 512, right? Which is around 64 times cheaper, which is around 64 times cheaper than a full causal attention layer. That's sliding attention, right? And the way Gemma actually implemented this is that, remember that there are 18 transformer blocks, right? So what they did is they had, in the 18 transformer blocks, they had 3 full attention blocks where we had the causal attention as I just showed you, and they had actually had 15 sliding attention blocks. So block number 1 was sliding, block number 2 was sliding, 3 was sliding, 4 was sliding, and 5 was sliding, but 6 was full attention. Then 7 was sliding, 8 was sliding, 9 was sliding, 10, 11, 12 was full attention. Similarly, 13 was sliding, 14, 15, 16, 17 was sliding, but 18th was full attention. So that's how there were 3 full attention blocks and 15 sliding attention blocks. Why did they do this? Again, there is a trade off, right? If you cannot look far back into the past, you're losing some context. But since the number of input sequences we are looking at one time is quite large, it's 32768, maybe this is a good trade off. Since with this trade off, you are actually saving 64 times the amount of parameters which you need to compute and save in the memory. This sliding attention is now being utilized by many language models because it seems to be a good trade-off between performance and managing memory and compute requirements. So I hope now all of you have understood these two things which I mentioned. What is the sliding window attention and what is the multi-query attention? As I mentioned at the start of this workshop, if you don't know what is the trainable query matrix, key matrix and value matrix, you might be thinking that why do we take WQ, WK, WV? What is this context vector exactly? So then I encourage you to refer to those lectures to gain a full understanding. But at least now you would have understood that okay, sliding attention is a variant of causal attention where one token should not look way back into the past but only slightly back into the past, and of course it is restricted from looking into the future. And multi-query attention is where I share content across multiple heads in my trainable keys matrix and trainable value matrix, and naturally then across the keys and the values matrix also, which come after the multiplication of the input with the keys and the values. Here again there is a trade-off, right? I'm saving the number of trainable parameters because I'm sharing the content across different heads. But why did you introduce multiple heads? To capture the different perspectives in a given sentence. Now that's fully lost. These are the, now due to these trade-offs, Gemma has so many, or fewer parameters, right? These are some trade-offs which they needed to make in order to have fewer parameters. Now what we are going to do is that we are going to understand rotary positional encodings. Then we are going to understand QK norm, feed forward neural network, and output layer. So there are four key aspects of the architecture which we are still yet to understand. So let's begin the journey to understand those four aspects now. All right, so let's come to rotary positional encodings now. The idea of positional encodings is not new. It was introduced in the original transformer paper in 2017. So let's say if you have a sentence like the dog chased the ball, it could not catch it. Now, if you take a closer look at this, it refers to the dog, and this it actually refers to the ball. So if you just use token embeddings, both of these, it will have the same token embedding. So you need to somehow encode information about the position as well. The position at which a particular token comes also plays a very important role. Before rotary positional encoding, what happened was there was this thing called absolute positional encodings, and that was actually added to the token embedding in this step itself. So in the input step, the token embedding was added to the positional embedding, and we got something like an input embedding, which was essentially then passed into the processor block. The main issue with this approach, which people figured out, is that it really contaminated the meaning, right? Because token embeddings refer to the meaning of tokens. Why would you add that to the position information? That diluted the semantic information which is carried by words or tokens. So then people figured out that why don't we add the information about position in the attention mechanism itself? In particular, if you remember the attention mechanism which we saw, we had the query vectors and the key vectors, right? And here is where we are actually encoding which token gives how much attention to nearby tokens. So here is where the knowledge of the token position actually comes into play. So why not actually augment these query vectors and key vectors with positional encoding? Since they are used to find the attention scores, maybe we can use these vectors and we don't need to alter the value vectors at all. Another thing which people realized is that here we are just adding token embeddings to positional embeddings, right? That's also changing the magnitude of the token embeddings. So instead of adding something over here, why don't we just rotate the vector? Why don't we rotate the query vector and the key vector so that the magnitude is maintained but the angle changes? So position information is included as a rotation, right? That's why it's called rotary positional encoding. So the way it works is that the main idea is to take the query and the key vectors and to apply the sinusoidal and cosine positional encoding to these vectors. Let me show you how that is done. So let's say if you have a query matrix, right? The dog chased another dog, and this dog and dog are at different positions, of course. So what we have to do is that if you look at the first query, it has four indices. If you look at the first query, the x1, x2, x3, and x4. In rope, what we do is that we first take the first two indices, which is x1 and x2, and we form a vector out of this, which is x1 comma x2, and then we rotate this vector. So this is one vector x1 comma x2. We rotate this vector. How much amount we rotate this vector? That's given by this 1 divided by 10,000 raised to 2I divided by d. What is I? I is the position, right? So this is position number 1, 2, 3, and 4, and d is the, so I is actually the index and d is the position, right? So the comes at position number 1, dog comes at position number 2, this 3, this 4, and this dog comes at position number 5. That's encoded by d. That's the position number. I is the index within a particular position, right? So if you look at position number 1, this is represented by 4-dimensional vector. I represents the index of that vector. So there are two variables here, the index across a vector, and then the position itself. Okay. So if you take x1 and x2 right now, let's say if this is the original vector x1 and x2, it's rotated by an angle theta, and that theta is given by this formula, which definitely includes position information. This is how the information of position is embedded, and without changing the magnitude, we just rotate this x1 x2, that gives rise to x1 dash and x2 dash, right? And x3 and x4 are also rotated. Can you see why they will rotate with a different amount? So x1 for x1 x2 and x3 x4, the position remains the same because the is at position number 1, right? So d remains the same, but the only thing which changes is I, the index. X3 and x4 come at a higher index compared to x1 and x2. So they will be rotated, and they'll be rotated by a slightly smaller amount because I comes in the denominator. So x3 x4 will be rotated to form this new vector x3 dash and x4 dash. So overall what happens is that this x1 x2 x3 x4 vector is converted into x1 dash x2 dash x3 dash and x4 dash. This is now a query vector or a key vector with position included or position embedded, right? So the position information is embedded through this rotation. So note that to include positional information, we don't add any vector to the query vector or the key vector. We just rotate parts of the original query vector, and hence we maintain its magnitude. And we avoid the vector polluting issue which was seen with sinusoidal encodings. And when I say sinusoidal encodings, that was essentially the point where you were just adding the encodings to the token embeddings. Here we are avoiding that. We are just taking the query vectors and the key vectors and we are rotating those, right? Now, some key points to note here is that, as I mentioned, the rotation, if it's the dog chased another dog, right? The rotation depends on two things. It depends on in the denominator we have 2I divided by d, right? So it depends on the index and it depends on the position. So let's take a look at one index for now. And if you increase the position, the rotation value increases. So higher positions lead to larger rotations. This means that closer queries have similar positional encodings. So the and dog are closer, right? So they will have closer positional encodings. But this dog and this dog are farther away. So their positional encodings will differ. You can see how positional encodings magnitude or the rotation magnitude increases with distance. This increases with position for a fixed index. Also check the lower indices oscillate faster with higher as compared to higher indices. So lower indices change fast with position, higher indices change slow. And the way to see this is actually not in these columns, but check the amount of variations, right? In these lower indices, there is so much change in the circle size. But in the higher indices, the circle size almost remains the same. So lower index quick oscillations ensure that the model captures small shifts. For example, if we have two sentences, I just told her the truth and I told just her the truth. These are completely different sentences, right? So the lower index fast oscillations capture the change here. Higher index components ensure that even with large position differences, the relationship is preserved. So Einstein developed the theory of relativity. This breakthrough reshaped physics. Breakthrough refers to theory of relativity several words earlier. So higher index low oscillations captures these long range context dependencies essentially. That's just a qualitative thing to worry about. But whenever I say rotary positional encodings over here when I say rotary positional encoding, what I essentially mean is that the position, the query vector, let's say, which is there, and the key vectors, they are broken down into groups of two, and these vectors are rotated by a particular angle based on the position and based on the index. So now if you have the dog chased the ball, it could not catch it. This it comes at a different position than this it. So the D in the denominator will be different for different its. So that's how their information will be embedded in the query rotation and the key rotation. This is the rotary positional encoding part. Okay. This is another key component which is implemented in the Gemma 3 270 billion architecture. They had rotary positional encodings and not absolute positional encodings. The sixth thing which we have to consider is the QK norm. Basically, what this means is that the same RMS normalization which we saw earlier, right? There is nothing new here. The same RMS normalization which we saw over here is now applied to the query vector and the key vector. That's all. So in the code, we are going to see, you will see QK norm, right? So it's as simple as that. Essentially, before calculating the attention scores, we apply normalization to the query and the key vector. That's all. So this step is actually simplest to explain. We apply RMS normalization to the queries and the keys before calculating attention scores. And the reason it's mentioned as a separate point over here is because this was not done earlier in traditional architectures which came before. So now I hope you understand this entire attention block, which is the brain of the transformer architecture, right? There are 18 such transformer blocks, and within each of these transformer blocks, we have the sliding window attention, which tells the attention scores matrix that for each token you have to not look into the future, but you have to not peek too far back into the past also, and that reduces the amount of attention calculations which we need to do. Second thing is multi-query attention, where the keys and the values share the content across heads. And the third thing, which is equally important, third and fourth, is rotary positional encodings. The keys and the queries are rotated to encapture or to encode the positional information. And finally, we have the QK norm. So keys and queries are actually normalized. RMS norm is applied before calculating the attention scores. Now we move to the next module, which is the feed forward neural network. Now here, what they actually implemented was, traditionally, a feed forward neural network which is implemented just is an expansion contraction layer, right? So if the embedding dimension is 640, you define an expansion block. Let's say that's 2048 in the case of Gemma. And then you just define a contraction block which brings it back to the 640 dimension. That's all what a feed forward neural network does. And you have an activation layer, activation which is the JLU activation here. So what they did was they had this similar mechanism where they had one neural network here, which, so in this one neural network, the 640 dimensional vector is expanded to a 2048 dimensional vector. It passes through the JLU activation, and we have a 2048 dimensional vector here. That's fine. But then they construct another neural network, which is again 640 to 2048. So the output is 2048 over here. We have an element wise multiplication of these two vectors that leads to a 2048 dimensional vector, and then again we have a contraction to a 640 dimensional vector. So this can also be called as an expansion contraction neural network which they have, but in the expansion step they essentially have two neural networks, and only one neural network which I mentioned on the left hand side has this JLU activation, but the neural network on the right hand side does not have any activation layer. Now, if you ask about why did something like this, it's the architectural design which they implemented. Probably they figured out that this will make the expansion contraction block more expressive, right? This definitely adds more parameters over here, and they were optimizing the parameters. Remember, they were always intended to have this model as small as possible, but here they chose to increase the number of parameters. They chose to add one more neural network over here, and this was across 18 transformer blocks, so that increased the number of parameters. But I think they figured out that if you just have one single feed forward neural network, why is this feed forward neural network needed? Is because it's because the expansion contraction allows us to explore a richer dimensional space and a higher dimensional space, right? But they figured maybe this was not enough, so they added one more neural network here, so the exploration could be even more richer in a higher dimensional space. That's the feed forward neural network part over here. And again we have an RMS norm after that. There are two things which I did not mention here, which are the shortcut connections or skip connections. Shortcut connections are added just to make sure the gradient flows faster, or rather the gradient has an alternative direction to flow and it avoids the vanishing gradient problem. The final thing which I want to mention is this output layer over here, right? And the only thing which I will say for now is the output layer actually converts the embedding dimension back into the vocabulary dimension for the next token prediction. Now, as you are going through these architectural blocks, I'm sure you must be confused about dimensions, right? Don't worry about that right now. I'm going to go through this entire workflow now, Gemma 3 270 million entire architectural workflow, where I'm going to show you exactly what happens with dimensions in the Gemma architecture. For now, I just need you to be in a state where you are comfortable with the concepts. You understand the concept of token embedding, you understand the concept of RMS norm, you understand the broad concept of multi-query attention, you understand the broad concept of sliding attention, you understand rotary positional encodings, you understand QK norm, and you understand the feed forward neural network. When I say in the output layer, the embedding dimension is converted to vocabulary dimension, I'll show you exactly how it is done. But until now, you should understand these main key conceptual blocks which are involved in the architecture of Gemma 3 270 million. This part until now, it's this step number 4 is one of the most difficult aspects of this lecture or the most challenging aspects. But if you have understood intuitively until now, you are now ready to move to the next step where we are still in step number 4, but now we are going to see this entire architecture workflow with respect to dimensions. This same workflow which I showed you over here, right? I'm going to do that workflow now with dimensions. So let's go into that right now. So in all of my teaching lectures, I always say that the person who has mastered dimensions will always find it very easy to understand LLM architectures or language model architectures, right? So we started this section by thinking about input tokens, right? And what happens to them when they pass through this entire transformer block. Now let me tell you with exact dimensions which Gemma 3 270 million actually had. They used a token embedding dimension of 640. That's the first thing to consider, right? So if you have four tokens like these, the first step is, which you have already seen in the input block, the first step is to convert these token IDs into embeddings, right? So what happens in the first step is all of these token IDs are converted into 640 dimensional vectors. So we have four input ID number 1, 11, 15, and 24. All of these are converted into 640 dimensional vectors as you have seen over here. Okay. So I've mentioned embedding size here deliberately so that you can keep track of the dimensions. So now this matrix now is of the size of 4 multiplied by 640. So it has 4 rows and 640 columns, right? That's the input block. Once we get out of the input block, we come to the processor block. And remember, in the processor block, the thing which we start out with is this RMS norm. That's the bottommost thing which we start out with in the processor block. Uh, Yeah, so we are starting out with RMS norm. Remember, RMS norm is an operation which is done vector wise. So there is no interaction between different vectors at this stage. So each vector is processed individually. So the dimensions remain intact. So after we apply RMS normalization, I've changed the tokens here a bit. Every effort moves you. You can visualize this with the same token IDs which we had earlier. RMS norm is applied, dimension remains the same, tokens have still not interacted with each other. Now, here is the step when things change a bit, right? Here is the step when we have the attention mechanism and we apply rotary positional encodings. Here is where neighbors suddenly get to know about each other. So, the input embedding vector is converted into something called as a context embedding vector. Here is where the dimension changes from 640 to 1024. The way they did this is that if you take a look at our attention mechanism here, right? So we had, I mentioned to you the query, the key, and the value matrix, right? And there is an output dimension. So they had an output dimension of 1024, and that's equal to the number of heads into head dimension. So they had a number of heads equal to 4, and each head dimension was 256, which you will see in the Google Colab code file which we have. If you scroll down below, you will see that Um, the embedding dimension is 640, which we already saw. Number of attention heads is 4, and the head dimension is 256. So the d out is 256 multiplied by 4. That's 1024. So d out is, this is d out. It's n heads into head dimension, which is 1024. Now, one thing which I did not show you in the attention mechanism is that there is also an output projection layer over here. The output projection layer over here brings the output dimension back to the 640 dimensional vector which we started with. And now this, the reason I say this is the place where the whole magic happens, because here is where neighbors know how much attention I need to pay to each other. So the context vector which we get over here is much more richer in value compared to the input embedding vectors which we had until now, because they had no clue about their neighbors. So let me just rub these. All right. So we are at this stage where we have this output projection. Then we have one more layer of RMS norm that retrains, that preserves the dimension. Then we have a shortcut connection followed by an RMS norm. So if you see, after two RMS norms are applied, number one and number two, we have a shortcut connection followed by another RMS norm. So that's what we are doing right now. We have a shortcut connection here followed by another RMS norm. So the dimension is again maintained. We have four tokens, each of which has 640 dimension. Then we have a feed forward neural network, right? Now in this step, in this feed forward neural network step, this thing happens, which I just showed you. Now you might be understanding why I use 640 over here, because when the vectors reach this stage, they have a dimension of 640. So there are two neural networks in parallel. In one, 640 is expanded to 2048, goes through J loop. We again have 2048. In the second, 640 is expanded to 2048. We have a dot product of, or uh, element wise multiplication of 2048 into 2048. That leads to a 2048. And then we compress it back to a 640 dimensional vector. So the output of this feed forward neural network is 640 dimensional. Then we again have RMS norm, and finally we have the shortcut connection, right? Now all of this which I have shown you, all of this, that is for one transformer block. The output from one transformer block will go into another one. So there will be 18 such transformer blocks chained together. There will be 18 such transformer blocks chained together, and the output of these 18 blocks which are chained together, let me rub this, the output which comes out of these 18 blocks then goes into my final layer, which is my output layer. So when we come into the output layer, again we have these four tokens with a 640 dimensional vector. The first thing which happens in the output layer, if you see, first thing which happens in the output layer is again RMS normalization, right? So we have the output layer, and we have RMS normalization over here. So it maintains the dimension which is 640. Now here is the critical step, which is the final output layer. Here is where we go from the embedding dimension to a vocabulary dimension, right? So we have this four tokens, but each of them have a 640 dimensions associated with it. So we multiply this with a neural network which has dimensions of 640 multiplied by 50257. So if you have a 4 times 640 matrix, and if you multiply it with a 640 times 50257, the resultant matrix which you will get will be 4. You will have 4 tokens, but now each will have 50257 dimensional vector. Okay. Now this is how we get predictions, right? And let me show you how we do that. Let's say if you have this is the first token ID, second, third, and fourth, and we have 50257 dimensional vector. So all of these are 5025 dimensional vectors. So the way we get the next token prediction as predicted by our model is that we take a look at the first row, right? So again, let's go back to the example which we started with in this lecture. We had this input output pair, right? And let me bring it over here. We had this input output pair. So now let's say, let me rub this a bit so that it's easily readable to all of you. Yeah, we have this input output pair, right? Now this input, which is token ID number 1, token ID number 11, 15 and 24, has passed through this entire architecture which we have seen, and what comes out is this 4 times 50257 dimensional vector. So the way predictions are made from our model is as follows. What we do is that in every row we are going to see what is that index which has the maximum value. So let's say that's index number 55 here. Then we are again going to go back to our vocabulary and look at the token which is corresponding to that index. So my predictions are going to be, let's say, token ID number 55 over here. Then I look at 11 row. I look at, let's say, here the maximum value is given for index number 6771. Then I look at 15 and I look at its prediction and I get that the maximum value is given at token number ID number 8. Then I look at 24 and then I look at that place where the maximum number is given and maybe that is 40,000. Right? So these are my predictions now and this is my ground truth data. Now we have the predictions and we have the ground truth data, and now the loss function is calculated between the predictions and the ground truth. I hope all of you have understood now what this input which is there, it goes through a very long journey. This input which we just saw, it goes through the input block, it goes through 18 transformer blocks in which it goes through all of these steps. It comes out, it has the RMS normalization, then it has the final output layer, and then it gets mapped, every token gets mapped to a vocabulary dimension. We take the token ID corresponding to the maximum value, and that's our prediction. This prediction is then going to be compared with the actual output and we are going to get the loss. I am going to tell you how we actually compute the loss in the next step. But until this time, I hope all of you have understood how we get the predictions, right? And now let us see how we get the loss. It's very simple how we actually calculate the loss. Let's say if we have these 4 tokens, right? The same tokens which we had seen, I have just given them some different names over here, and each of them is mapped to a vocabulary size of 50257. The first thing which is done is that we apply softmax to every row so that each row now sums up to 1, right? And for every input token IDs, I know my output tokens. I know the ground truth. I mean, the ground truth, let's say it's 23, 3881, 11223, and 15. Let's say that's the ground truth which I want. Now, how will you get the loss? And let's say your maximum values are for these random token IDs which belong to these tokens. So definitely your model is not good. Then how do you get the loss? You can pause here for a while to think. Let's say if you look at row number 1 now, you want the output to be 23, right? So you want the token ID number 23 to have the maximum probability. Ideally, you want this probability to be equal to 1. Similarly, but let's say the probability is not equal to 1, that it's 0.2 for token ID number 23. Similarly, for the second row, you want the output to be 3881. So ideally, you want the probability at 3881 to be the highest, but let's say it's very bad, it's 0.1. For 11223, you want the probability to be 1 again, but it's, let's say, 0.05. And for 15, you want the probability to be high, but again, let's say it's 0.3. Now, all of these probabilities, which I'm calling as P1, P2, P3, and P4, ideally you want them to be 1. You want P1 to be 1, you want P2 to be 1, you want P3 to be 1, and you want P4 also to be 1. Because when they are 1, you also ensure that the other probabilities are close to 0, since every row probability now sums up to 1. How do you ensure that P1 is 1, P2 is 1, P3 is 1, P4 is 1? What's the loss function which you can think of? So here is where the cross entropy loss comes into the picture. I am going to use the negative log likelihood. So the loss function I am going to define as negative 1 by 4 log P1 plus log P2 plus log P3 plus log P4. Essentially what I'm doing is that I want probabilities to be close to 1, right? So if it's 1, it will be 0, but as it diverges from 1, my loss becomes very high. That's how the cross entropy loss is actually calculated for these output tokens. So even when we have, in this case, I have my predictions, right? So what I will do is that I want my outputs to be 11, 15, 24, and 63. So at these positions, I will find P1, P2, P3, and P4, and I will try to minimize my cross entropy loss. I won't use these positions in my loss at all, because for these positions, if my probability is maximized to 1, for these positions it will automatically become 0. That's how the loss function is actually calculated. This is the cross entropy loss, right? And remember, until now we have seen only for one input output sequence of a batch, how do we get the loss? But ideally what happens is the whole batch is passed. So ideally what will happen is that this entire batch which you have seen over here, this whole batch, so I'm just going to take this right now. So what I have shown you for one input here, right? This entire batch, right? So all the inputs of this batch will go through this exact same journey. All the inputs of this batch will go through the exact same journey, and finally we'll just take an average of all the losses basically. So one input you understood how we get the predictions and how do we get the loss, right? The cross entropy loss. The exact same thing is done for all the other input sequences in this batch. So one input goes through the architecture, we get the loss, second get the loss, third get the loss, fourth get the loss, and then we take the mean of all the losses, right? And once we get the losses for one batch, then we are in a position to do back propagation, which we are going to see in the next step. So let me actually set the stage for what we are going to see in the pre-training step. So until now, what we have done is that we have a batch. We have a batch. That batch goes through the entire LLM architecture, and then we have a loss for this entire batch, let's say, which I'm calling L. Now what is done is that, let's say we have 100 million parameters, right? P1, we have P2 dot dot dot, we have P 100 million. And now I'm going to do a backward pass, which means I'm going to implement uh, gradient descent based procedures, and I'm going to update every single parameter. So P1 will be equal to P1 minus alpha times partial derivative of L with respect to P1. This is just simple vanilla gradient descent which I'm showing over here. And P 100 million will be P 100 million minus alpha times partial derivative of loss with respect to P 100 million. So that's how I will update my parameters. Once the parameters are updated, I will get a new batch. So once the parameters are updated, I will get a new batch. How do I get this batch? I get the batch from the get batch function over here. Okay. So in the next step, we are going to see exactly how do we do this pre-training, what is the optimizer which we are going to use, what's the step size which we are going to use. But before that, I want to show you in the code, essentially the different things which we have defined in the architecture itself, right? So the best way to start looking at the code is this class Gemma3 model, right? And if you look at the forward method in the class, you'll see multiple things which are happening. First, what we do is that we actually convert the input IDs into token embeddings. That's exactly the first step which we saw, if you remember. The first step which we saw is converting the input IDs into token embeddings. Here we just multiply with the square root of embedding dimension, which is square root of 640, to make sure training becomes a bit smoother. Okay. Then we are creating the global mask and the local mask. What is the global mask and what's the local mask? Essentially, the global mask is causal attention, which we saw. Okay. The global mask is causal attention, which we have seen over here. Right over here, that's the causal attention. And the local mask is this sliding attention mask. So we define both of these masks. We define the local mask and we define the global mask as well. Okay. So first what happens is that we get the token embeddings, and then we immediately go to through the processor block. This is the same thing which we saw in the architecture, right? Once we get the token embeddings, we immediately go into the processor block. Now let's see what's there in each transformer block. So I'm going to this class called block right now. Yeah, here. This is where my each transformer block is defined, right? In each transformer block, what I have is I first apply normalization, then I check for the attention type. If the attention type is sliding, I apply the sliding mask. If it's global, I apply the global mask. Okay. Then what I do is that I apply one more normalization and shortcut connection. So until this point, I have finished applying the first normalization. I get the sliding window. I apply the attention layer, and then I apply the second normalization layer. And then I come to this path where I have one more shortcut connection. Then I have this another layer normalization. I have the feed forward neural network, then one more RMS norm, and then a shortcut connection. So you can think of it as divided into two steps. In these steps we are implementing the first RMS norm, the sliding window, and the second RMS norm. And in these steps what we are implementing is that we are implementing the this RMS norm, the feed forward neural network, and second RMS norm. And in the middle, we have the shortcut connections. That's exactly what's being implemented over here. Now, you might be seeing this cos local and sine local, right? That's essentially the rotary positional encoding. So, if you scroll above, you will see a section on rotary positional encoding. So, when you apply the rope, we have already seen how exactly to apply the rope, right? Over here, if you remember, we have seen how the rotary positional encodings are applied. So this piece of code which I have just shown you does the same thing. So 1 divided by 10,000 raised to 2I by d. That's the same thing which is happening over here, where theta base is equal to 10,000. Okay. And why we are considering the context length over here is because the number of maximum positions we can go till is the context length, right? If you check over here, the number of indices we can go till is going to be, the number of positions which we can have, that's restricted by the context window. We cannot have more positions than the context window. So basically, in this step, if you look at this step, yeah, in this one step, multiple things are happening. In this one step, we apply the mask, which is a sliding mask. We apply the rotary positional encodings, and in this step, we apply the multi-query attention as well. Because if you take a look at the attention block over here, if you take a look at, it's called grouped query attention, but actually in this case it's multi-query because we are sharing it across all the heads. So if you take a look at this attention mechanism, we have query, keys, and the values. And before actually, so we have the queries, keys, and the values. We apply the normalization to the queries and the keys vector. Then we apply rope to the queries and keys, right? And then we get the attention scores, we get the attention weights, and then we get the context vector matrix. These are the exact same steps which all of us have seen in the multi-query attention part. And I'm deliberately going a bit fast through these steps because if you explore the code later and map it to the lecture notes, you'll find that they are exactly the same. Okay, so we started at this Gemma 3 model and we started at this forward block. Here we did the token embeddings and we went through the transformer block. In the transformer block, we had multiple things. If you scroll above in the transformer block, we had first we had the normalization, which is the RMS norm, which I think is mentioned over here. Then we had the attention. Then we had another RMS norm and a shortcut connection. Then we had another RMS norm, feed forward neural network. Then we had another RMS norm and then a shortcut connection. The attention mechanism is where, if you take a look at this grouped query attention, here is where we apply the rotary positional encodings over here. And here is where we also do the sharing across the different heads. So if you see, the sharing across different heads is actually done in this part of the code. And if you scroll above, you will also see a class for RMS norm over here. That's the same class, RMS norm class, which is used um, for the different RMS norm mechanisms which we are following over here. So, for example, if you see, there is this the RMS norm mechanisms are called different. So, this is called pre-forward RMS norm, but it's just the same RMS norm. So, we are calling it by different names: input layer norm, post attention layer norm, but it's the same RMS norm class. If you scroll above, you'll see that this is the same RMS norm class which we have seen on the whiteboard. Okay, so all the building blocks of this code might look a bit complex to you, like what is this mask global? That's the causal attention. What is this mask local? That's the sliding attention. I think everything which we have covered on the whiteboard, you will be able to trace back to the code. Just make sure you start through the Gemma 3 model class. You go through the forward mechanism or the forward pass in this class and then try going backwards, right? So here what's happening is that we go through the forward pass, we get this output logits, and then we have this cross entropy loss. And then we are returning logits as well as we are returning the loss. That's what's happening in this step. And here we are defining the configuration, right? So the vocab size is 50257. The context length for Gemma 270 million is 32768. Embedding dimension is 640. Number of heads is 4. These are the number of attention heads. Number of transformer blocks is 18. QK norm is true, which means we are going to do RMS norm on the query and the key vector before we take the attention scores. Number of KV groups is 1. This means it's multi-query attention. We are sharing everything across uh, the heads. These values are for root tree positional encodings. And as I said, in the 18 transformer blocks, 15 of them have sliding attention and 3 of them have full causal attention, as I mentioned. That's the only thing, this is the only configuration which we need to know. Okay. Uh, and this estimate loss function, what it's actually doing is that it first gets the batch. So it gets an input output pair from the get batch function which we have already defined over here. It gets the input output pair from this function, and then what it is doing is that it passes the input through my model. It passes the input and the output through my model. So then it goes through all of these steps which we just discussed. The input, all the input from my batch goes through all of these steps which I just showed you, these all steps, and what comes out is the output, and also what comes out is the loss. Because remember, here in the forward pass we are also calculating the loss. Then we get the loss for each batch, and then we take the mean for the entire batch. So that's the loss which we are getting, and then once we get the loss we update the parameters, right? So now step number 4 is finally over. This was the largest step in this lecture, and now we are ready to proceed to step number 5, which is the pre-training step. I promise only two more steps are remaining: pre-training and inference. Thanks everyone, and let's see in step number 5. In the pre-training pipeline, I am going to discuss some key things which will help our pre-training, and you can use some of these insights for pre-training larger models as well. The first thing which we are going to do is doing something called as mixed precision. So what this does is that it lets the model use float 16 where it's safe and falls back to float 32 where needed. For example, matrix multiplications um, can use float 16. They can be fast and stable. Dropout or JLU activations can use float 16, but for softmax, cross entropy loss, weight updates, we will stick to float 32 for stability. So that's one thing which if you scroll down in the code, you will see that when you come to step number 6, the SLM training configuration, you will see that we are using this mixed precision framework over here. Um, and it's called torch.am.autocast. So if you see, over here. See, this is where we are actually using that mixed precision framework. The second thing which is important to understand is something called as gradient accumulation. So if, let's say, if we want to train with a higher batch size, let's say 1024, but your GPU only fits a batch size of 32, let's say, for an example. Batch size is one of the fastest way or one of the most common way you run out of memory on GPU. So what you can do is that you can do a small trick. So you divide your batch of 1024 into 32 micro batches. So each micro batch size will also be 32. So you do micro batch 1 and you compute loss on only 32 examples. You store that gradient, uh, and then you go to the second micro batch. So at each time point you are only storing one micro batch in the GPU. You get the second micro batch, you get its gradient. Similarly, you get all the 32 micro batches, you get their gradients, and then you divide it by 32. That kind of simulates finding gradient for an entire batch. This is called as gradient accumulation. And the number of steps here we mentioned 32, right? It's the total batch size divided by the micro batch size which you want. And here the gradient accumulation steps which we are going to set is equal to 32. So after every 32 such steps, parameters will be updated. And how are the parameters going to be updated? The parameters are going to be updated using the ADAM-W optimizer. And we are not going to use a fixed learning rate. We are going to use a learning rate schedule which looks like this. We are going to use learning rate warm up plus decay, just something like this. So we'll start with a higher learning rate, and as we get into good spaces in our loss landscape, we'll decrease the learning rate a bit. So it's a mix of exploration initially and exploitation later. That's the learning rate schedule which we are going to have, right? So these are some tweaks which you will see in the code. The whole pre-training pipeline essentially looks like this. For each iteration, I'm going to choose X and Y. How are we doing this? Through the get batch function. So if you scroll up in the code, you will see that there is this get batch function, right? There is this get batch function. So we are going to use this function to get the input and the output pairs. That's going to be X and Y. Once we get the input and the output pair, we are going to pass X through the model to get the logits. And that's actually done in this estimate loss. In this estimate loss, we get the X and Y, and then we pass the X and Y through the model to get my logits, and I also get my loss. Then I will back propagate my loss, which means that I will use the ADAM optimizer and update my parameters. And I will only update parameters, by the way, after I've done gradient accumulation and reached these many number of steps. Then I will update my learning rate, and then I will evaluate and save best model. So I'll keep doing this for multiple number of iterations. That's going to be my pre-training loop. So if you look at step number 6, that's defining the training configuration part 1, we are going to be using the maximum iterations. You can start with even 60,000 iterations. I'm just going to show you few iterations live during code. I'm not going to show you the entire iterations because that takes time. In my experience, 150,000 iterations take around 8 hours on A100 GPU. 60,000 iterations would take around 3 hours on an A100 GPU. All right, and for the sake of simplicity here, what I've done is that I've set the batch size to be 32, and the context window or the batch block size I've set to be equal to 128. You can change these parameters to the actual values if you want. Everything else I've used as it is from the Gemma configuration. Okay, the only things which I've changed from the Gemma configuration is the vocabulary size, and then here I've changed the context window size slightly just so that I can demonstrate this whole training procedure to all of you. So this is the SLM training configuration part 1. If you scroll down below, you'll see SLM training configuration part 2. This is where we actually define the learning rate. Remember, I mentioned that we are not using a static learning rate. We are using this kind of an exploration exploitation type of a learning rate ramp up curve. And the optimizer which you are using is ADAM-W. Other parameters, the gradient accumulation steps is 32. We are using this mixed precision framework for faster computations. Please keep into mind these computational or the steps which we are doing to make sure that the computations are done in an optimized manner. And this is our main pre-training loop which I want to explain to all of you. So first, it runs through the different iterations. As I mentioned, we'll first call this estimate loss, because the estimate loss function, uh, which is here, it gets the batch, it does the forward pass, and it gets me the loss. So I'll call the estimate loss function, I'll print my loss, and then I'll do after this point I'll do back propagation. So once I get the loss, I'll do gradient accumulation number of steps, and then I'll do update. So this scalar dot update is essentially doing updation of the parameters, right? And then I'll go through this loop once more. Similarly, I'll keep on doing this until I do maybe 150,000 iterations, or you can even simply set it to 60,000 iterations for now to get started with. As you can see here, these are the exact same steps which we have done in the code, which we have written on the Miro board. What I'm doing in the code is nothing different from what we have already seen on the Miro board. So for each iteration, choose x and y, pass x through the model to get the logits, compute loss between logits and y, back propagate the loss, accumulate the gradients till we reach the gradient accumulation number of steps, update parameters, update the learning rate, and then evaluate and save your best model. So as you can see, I'm trying to run this live. My runtime got disconnected for some reason, but now we are still stuck in this train.bin part. It's going to take 4 to 5 more minutes. So I'll come back here after this train.bin and validation.bin is created. Then what we have to do is that we'll run the live training, and the last thing to see is the inference. So I'll see you in the next part. All right. So now the last thing which is remaining for us to do is actually see the live training in action. And as you can see, the most time consuming step, writing the training and validation.bin, has been done. Uh, the model architecture has been defined. So you can see from this tick symbol here that the model architecture has also been defined. Configuration is defined, loss function is defined, training configuration part 1 and 2 is defined. Now all we need to do is that make sure we need to run our iterations, right? So first, let me show you the results which I've got. So here you can see that I have run around 150,000 iterations earlier, and my loss, training loss and validation loss, both have converged and reduced very smoothly. In fact, if you plot the training and validation loss, it goes down to less than 2. And there is no sign of overfitting here, which is an excellent thing to do. Uh, there is a sign of overfitting if the validation loss becomes much higher than the training loss, which is not the case over here. So I can safely conclude there is no overfitting. Let me show you some live training over here. So you see the training has started for me, and I'm doing 150,000 iterations. And on my A100 GPU, it's around 7 iterations per second. So with this rate, it's showing 6 hours, but it always takes more than that. You can assume 7 to 8 hours for these many number of iterations, right? Now, once your pre-training is done and your training loss has decreased and your validation loss has decreased, the last thing for all of you to do is inference, right? And the way inference is done is that the model parameters are all fixed, right? So what you have to do is that you have to define this function called as generate. So if you look at this class Gemma3 model, you will see a function which is called as generate over here. What this does is that it takes in a bunch of tokens and generates new tokens. The way inference happens is usually is in this format. Let's say you have an initial set of tokens, right? You pass it through the Gemma architecture, and then you get the next token prediction. You get the next token which is predicted. How is the next token predicted during inference? Well, if an entire input is passed, and if you get these, you get the output for every input token in that sequence. You only have to see the output token for the last in the sequence, right? So, for example, if this is the input, every effort moves you during inference. If you want to predict the next token, you don't want to see what's the next token which comes after every effort and moves. You only want to see the next token which comes after you. So you take a look at its output logits vector and take a look at the index which corresponds to the highest probability. That's our next token. So you get the next token, you append it to the input, right? So now my input is appended with the next token. Then I again pass it through the Gemma. Then I get my next token. Then I again pass my next token to the input. And then I again pass it through the Gemma architecture. That's how the next token prediction works during inference, right? This is exactly what we are going to do right now. And this continues until the maximum new tokens has been reached. So you see maximum new tokens is a parameter over here. And until maximum new tokens has been reached, this iteration will actually continue to happen. So if you scroll down below and let's see over here, and here I'm setting maximum number of tokens to be equal to 200, right? Here I'm also showing you how to load the best model parameter. So basically, we have a file called best model params.pt. This file will ultimately save those parameters which give the lowest loss. So even if you close this session after the training is done, next time when you come, all you have to do is just load this best model parameters, and then you can generate new tokens from this model. So my sentence which I passed is once upon a time there was a pumpkin. I passed it through this entire model which we have assembled right now, and then I generated new 200 new tokens over here. So the result is once upon a time there was a pumpkin. This pumpkin was very special. It was a big special pumpkin because it was real. Everyone was so amazed by the green color. Now I really want you to pause and appreciate what we have done here. Within 270 million parameters, our model only had 270 million parameters to work with. And remember, it started with these bags of train.bin and validation.bin. We are not teaching the model grammar. We are not teaching the model meaning of words. We are just training the model to do a next token prediction task. And through this simple training, the model actually understands English language. How beautiful is that, right? We never told the model that in English language there is subject followed by word followed by object. The model has derived all of that from the data and from the architecture which we have assembled. In fact, all of these are highly coherent sentences. It was the sound of war, a dangerous animal, and it was coming from behind the field. They sat in their spot and watched the birds move in the sky, etc. Again, if you give the sentence that a little girl went to the woods, the completion is the little girl went to the woods alone. She looked around and the animals had been playing a game. Then she said, I want to tell you a secret. The little girl was surprised. Now, none of these would be in the actual data. This is what we have generated through our model, which we have trained from scratch. There is a lot of satisfaction in training an entire model right from the ground up. And I hope this tutorial gave you that satisfaction yourself. What you can do is that you can also upload your model to Hugging Face after this point. So if you have a Hugging Face account, you can simply, so if I go to my Hugging Face right now, and you can simply upload your model over here. So see, this is the model which I've uploaded over at Hugging Face. So if someone wants to use this model, they can just download the best model parameters. That's the power of the open source community. This brings us to the end of today's workshop. I hope it was useful to you and I hope that you learned a lot. As a quick summary, today we have covered 6 steps: dataset loading, data tokenization, input output pairs. The major thing is, which took a lot of time, is assembling this Gemma 3 270 million architecture, right? The new things which we saw over here are rotary positional embeddings, sliding attention layers, multi-query attention, and output layer. In fact, this whole architecture, if this is new to you, this would be a good time for you to revise this and understand how modern LLM architectures are built. Earlier, there was a standard normalization. Now things have moved to RMS norm. Earlier, there was absolute positional encoding, which was added to the token embeddings before we go to the transformer block. But now we have rotary positional encodings along with QK norm. Earlier, all the attention layers in every transformer block had a causal attention, right? which looked something like this, had a causal attention mask. We cannot peek into the future. But to save computational time and memory, modern architectures are switching into the sliding attention, where here actually they had 15 sliding attention blocks. So around 60% of the whole architecture, in fact not 16, about 80% of the whole architecture is sliding attention blocks, and only 20% is the causal full attention blocks. That's a change which has happened. Grouped query multi-query attention is also a change here. When there are only few heads which are sharing values, it's called group query attention, but here all of the heads are sharing values, so it's actually multi-query attention. And then after that, we saw pre-training, where we saw different things like Adam W optimizer, we saw gradient accumulation steps, we saw mixed precision framework, and we ran the entire pre-training loop. And finally, we ran inference, and we saw how a 270 million Gemma 3 architecture model gave us good inference results on this specific data set. I hope you can use this tutorial to build your own foundational models from scratch, because that is where all the fun lies, rather than just directly using ChatGPT. Thanks everyone, and I look forward to the next video in this series, which will be building GPT OSs from scratch. Then we'll build Kimi K2 from scratch and also build Quen from scratch. Thank you.